Good day. Today I'll be discussing heat conduction. I'll be deriving a simplified form of equations that are very useful in solving heat conduction problem. Now let me start. Well, the idea of transfer process is generalized by this equation. It says that the rate of a transfer process is equal to the driving force over the resistance. Okay, this equation is very famous for the Ohm's law, which actually states that the current is just equal to the voltage over the electrical resistance. Current could be thought of the rate of transfer of electrons is equal to the voltage driving force over the resistance. Okay, and for heat transfer, this a similar an analogy could be made, which states that the rate of heat transfer Q is just equal to the driving force. In this case, difference in temperature over the resistance, the thermal resistance. This is electrical resistance and this will be thermal resistance. Okay, so let me derive this after with the idea of Fourier's law for heat conduction. Fourier's law states that Q over A, or the heat flux, is equal to the negative of the thermal conductivity times dt dx, where T is the difference in the temperature, x is the distance within the material. Now, this one is the law that actually governs conduction process. And let me transform this into this form, the general equation for transfer process. Now, let me solve for the application of Fordy's law for a flat wall or a flat slab. Okay, we have here like a wall of constant cross-sectional area where heat is flowing from left to right. Okay, heat flows the left part of the wall and it flows out to the right part of the wall. So like heat is flowing at rate Q. What comes in will be the same amount of heat that will flows out, assuming that we are in a steady state condition. Now, this wall will not just readily allow the heat to pass through. This will offer some what we call resistance. Okay, this wall has certain resistance, and for this amount of heat to pass through, there must be a certain thing like the driving force that drives this flow. We know that conduction will only happen if there's a temperature difference. So we say here that T here at the left hand side is T1, at the right hand side is T2, which means T1 must be higher than T2 for the heat to flow by conduction. Now, this wall of certain thickness delta x, the thickness of this wall is delta x, and then this wall is of area, the area of this wall is A. And when we say that area, the area where heat flows, in this case, this area, okay, where perpendicular to the flow of heat, that area is A. That area is A. Now, the Fourier's law in this case will just turn out to be, well, Q is constant because you know we are in a steady state process. What the heat that flows in is the same as what flows out. Area is also constant, and K, the thermal conductivity, meaning this material has a certain thermal conductivity K, and it's certain characteristic of that certain material. And if it's an insulator, then K is low. If it's a conductor, then K is high. And then the idea here is this is constant, Q is constant. And if we try to integrate this equation within, so that's constant, and we integrate that into this flat wall, we'll have here negative K dt and integrate that. Since this is constant, we can just put it out and then integrate this. At the left hand portion, shall we say this like this is your x1, the right hand side is x2, and x1 the temperature is T1, at x2 the temperature is T2. It will lead to this equation. Q over A will then be equal to K, the conductivity divided by this one will just become what? X2 minus X1. And then the integral of dt taken from t1 to t2 will just be equal to t2 minus t1. But with the negative sign, it could be written as what? T1 minus t2. And by this time now, we can rearrange this equation derived from the Fourier's law. So that it would look like this one, the general transport process equation. So if rearranging, isolating Q on the left hand side and T1 minus T2, letting that to be equal to the delta T, T1 minus T2 here, and multiply the A, the both hand side, but putting that in the denominator, it will then become what? X2 minus X1 over Ka. I simply, such more or less multiply everything by A. So A will be here, and I flip this one so that this will be placed in the denominator. So it's just a little mathematical operation in there, and then that will lead me to this form. And this can then further be rewritten as equal to delta T over R. Okay? Like I call this as my thermal resistance. In this case now, R will simply be equal to this. The thickness, x2 minus x1, and over Ka, the resistance to heat flow, and T1 minus T2, the driving force. This is what drives the flow. And thinking of conduction as this, Q is equal to delta T over R, will more or less simplify our solution to most problems, because this equation will prove to be very useful um, in our solution. So let me rewrite this equation for conduction. Okay, let me just drag this down a bit. Okay. So for conduction, we now have Q equal to delta T over R, where R is simply equal to x2 minus x1 is just a thickness of this wall, or that slab, delta x over Ka. And this is not that difficult to memorize really. Resistance could be just thought of, well, the resistance to flow, meaning it resists the flow. Well, if the slab is thick, meaning it offers a lot of resistance. And if it's what? And if it's what? If it's a big area, then well, heat could flow through a bigger area, so well, it could have a free flow of heat through there because the area is big. That's why area is in the denominator, because it reduces the thermal resistance. That's why if you want to protect yourself, you don't want to heat to flow out of your body. Normally during cold weather, just like this now when I'm recording this, you need to what? Reduce your area of heat transfer. So, and K, this is conductivity. Of course, conductivity inverse is reciprocal to what? To the resistance, meaning the higher the conductivity, the smaller is the resistance. That's why it's in the denominator. So memorizing this is not really that difficult because it has some, physical meaning. Resistance is proportional. The thickness, the bigger the thickness, the bigger the resistance. The area, the bigger the area, the smaller the resistance. And the conductivity, the bigger the conductivity, the more conductive it is, the smaller the resistance. It's in the denominator.